So who was in Scott's talk that was just in this room? So my talk is just like his, except it's about OO. And I'm using dynamically typed language for examples. But seriously, it's just like his. So I'm Sandi Metz. I am a woman of a certain age. I spent 35 years going to my day job and writing code, and then I accidentally wrote a book. And that was like a bomb went off in my life. And so after that, for the last 6 years or so, my job really has been to travel and teach short courses in OO. Like when I make money now, it is because that's what I'm doing. And that means that, hey, nothing happened when I hit click. Oh, I'm an idiot. Here, stand by for a minute while the speaker gets their act together. It means I'm spending a lot of time away from my dog. Now, I used to be one of those people that was like, speak to the hand about your dog, right? And then I got a dog, and I'm like totally booked by my dog. So I'm using this as an opportunity. My dog's actually with me on this trip. So I'm not really missing him so much, but I digress. So, like I said, I wrote this book. It came out in the fall of 2012, and on the basis of that, people started asking me to come to their shops. And so now the short courses that I teach in OO mean that my life consists of, instead of knowing a lot about one big application, what I do is I go see other people's applications, very large applications for big teams of programmers often, 10 or 12 or 15 times a year. And so it's a really different perspective about what the state of code looks like when all of a sudden you're diving into people's shops and seeing what they're doing. And everywhere I go, people have problems. And I thought for a while that, of course, that it was just, self-selecting, right? People don't call me if they think things are perfect. And so I was like, well, maybe just I'm seeing problems because of the type of work I do. And so I started asking my friends at conferences, after a while I started figuring out, because I have the leisure now to think of code as a whole unit, applications as a whole unit, I started thinking that I understood what the problem people were having was with OO. And so I started asking my friends at conferences, are your apps like this? And they were like, oh, that. Everything is, like everybody has that problem. It's not just people who call you. Like even people that don't call you, their OO looks just like that. And so I love OO. Like I'm the OO guy, and I'm the dynamically typed OO guy. And I think of OO as being really easy and very effective for the problems it solves. And I freely admit that it doesn't solve every problem, but it breaks my heart when I spend so much time in shops where people have OO that's just killing them. It is absolutely just killing them. And what we're finding now, I think, is that, with this sort of introduction of functional, which I love for the problems I think it solves, like there's a pendulum swinging where lately, if you get on Medium or you read the news, there's a lot of hating on OO. Right, which happens, like types are in again. Like for a while, dynamic typing was all the thing. For a while, inheritance was all the thing, like 20 years ago. Now it's like, oh, nobody uses inheritance. So we do that thing where we turn the new thing up to 11, and then we grow to hate it, and then we turn the next new thing up to 11. And I see that sort of happening in the OO world right now. And so today, I'm going to talk to you about the sort of overall generic pervasive problem I see in most object-oriented shops. And I'm going to tell you what's wrong, and I'm going to show you how to fix it, so that you can go home and fix it in your apps and teach other people this thing. There's a lot of pain out there that it's unnecessary for us to be suffering. And so today's talk's in 4 parts. First, I'm going to describe the problem in words, and then I'm going to show you the problem in code. My examples are in Ruby, which is super readable, so don't worry if you don't know Ruby. And then I'm going to describe the solution in words, and then I'm going to refactor the code we have to show you how the solution will look in code. So let's get started. In this first part, I'm going to introduce 4 apparently unrelated but deeply connected ideas. So I'm going to take you through each of the ideas and then combine them all into sort of a grand theme. And the first idea is from a guy named Martin Fowler. He calls it the design stamina hypothesis. And he uses this chart to illustrate it. Now, look at it in pieces. So the vertical axis is for cumulative functionality. It's like how much you get done over time. Time is on the horizontal axis, so time is passing from left to right. He draws 2 lines on this chart. That orangish one is how much you get done over time if you do design. And the blue line is how much you get done over time if you don't do design. Now, as you can see down here, early on in time, it's probably a bad idea to do a lot of design. You don't really know what your app's about. It's a waste of effort to do design. But there comes a time that if you continue, if you don't do design late in the project, then you're also wasting money, right? So what you really want, what we would like to do, if you want to be most efficient about writing code, you want to be on the no design line up until this inflection point, and then you want to start doing design as soon as you know enough about your application to know really what it's about. And what that means is here, this is an inflection point where you should change how you write code. You should change how you do business. The problem, of course, is that it's really hard when you're living with your app on a day-to-day basis to know exactly where that inflection point is. And if you start out following the design stamina hypothesis and you're doing no design, it's really easy to end up way out here, and where velocity is dropping to 0. This is when people call me. All right, but many of you are probably if you're doing OO, many of you are probably you've already crossed the inflection point and you're doing business the old way and you're finding that your velocity is slowing. All right, that's idea 1. Here's idea 2. I made this up. It's another chart plot space. So here, change is on the vertical axis. If code is easy to change, it's at the bottom. If it's hard to change, it's at the top. Understandability is on the horizontal axis. Things that are easy to understand are on the left. As you move to the right, it's harder to understand. In this space, a simple procedure is the easiest thing. It's easy to change, and it's easy to understand. By simple procedure, I mean it's short, and it has no conditionals. Any kind of script that's short and has no conditionals belongs there. If you took something that you could write, if you took a problem that you could write, that you could solve using a simple procedure, and you turned it into OO, it would make it harder, right? OO uses messages. Messages add levels of indirection. Indirection is hard for humans to understand. Messages seem to give us changeability. But the truth is, if you can solve a problem with a simple procedure, you should not be writing OO. OO is harder. It adds complexity. And so in that case, OO, even if you get your OO perfectly correct, it's going to move it along the right of the difficult to understand scale. There's going to be more things, and there's hops between them that you can't see in the code. All right. The problem with simple procedures, like you might feel like you could start out with simple procedures. The problem with simple procedures is they don't scale. Over time, they get big, and they accumulate conditionals. So it makes them really hard to understand. They move far up in the right-hand corner of this chart. The only thing that's worse is if you take your simple procedure and you do what I like to call faux-O. So you take that 5,000-line class that has many, many conditionals in it, and you chop parts of it off, and you hide them in classes you make up somewhere else. All right? You don't really get the model right. You just break it up in small pieces and add levels of indirection with message sending so that you can punish future maintainers. All right? That stuff is super hard to understand, and I know that a lot of you, the people in here who are doing OO, are probably living with that state right now. Like hiding some of the code somewhere else does not make it OO. All right, that's procedures versus object-oriented code. The third idea is about churn versus complexity. It was made up by a guy named Michael Feathers who wrote Dealing Effectively with Legacy Code. He wrote a blog post a number of years ago where he drew this chart. I added that green line. It's another sort of plot space. Code complexity is on the vertical axis. Churn, or the number of times a file is changed, is on the horizontal axis. You could take every class in any application you have and give it a complexity and churn number, and that means you could put a dot or a little X, as he's done, for it on this chart. Now, I drew that green line. My contention is this. In a well-designed OO app, if you plot churn versus complexity for all your classes, what you're going to see is the points cluster around that green line. What this means is over there hard on the left, you have some files that are really complicated, but they hardly ever change. And on the lower right means you have files that change a lot, but they're really simple. That's how you want your OO to look. I taught a class at a place where they They have Ruby code that is a port of some PHP code that takes some kind of notation and generates sheet music. And it's a nightmare. I mean, it's a bunch of super long methods. It's completely not understandable, but how often does the way you generate sheet music change? Right? It doesn't really matter. I mean, they had some code that was a terrible mess, and we don't care because it does not save us money to fix it. So it's okay for things to be messy and highly complicated as long as they never change. And it's okay for things to change a lot as long as they're simple. However, and so what you can guess that is the code that hurts. The code that is really complicated and changes a lot. So if you have something that plots to that corner of this chart, that's where trouble is in your app. All right, one last idea. Again, this is mine. I think the only things the things that matter to you are the things that are hurting you the worst. And I'm going to illustrate this with a couple of screen snapshots from Code Climate. Code Climate is a product that does static analysis of people's code, and it produces all kinds of information about the quality of your code base. They have buried down there on the Code Climate stuff is this churn versus quality chart. You can think of this as Michael Feather's churn versus complexity chart. Complexity is on the vertical axis, churn is on the horizontal axis. Since Code Climate will run for free against open source projects, I went and looked at the churn versus complexity chart for some well-known open source projects. Now, so this is Angular. Code Climate gives things a letter score like a classroom score. So this thing is a low C. Its GPA was a 1.8. Notice that these dots map pretty well to that green line, except there's this. Let's look at one that's slightly better. Here's Discourse. Discourse is scored a 2.58, like a high C, near low B, which is a pretty good score. Notice there's a nice tight clustering around the green line, except this. Here's GitLab HQ. This is the best score I got for you. This is a good solid B, which the Code Climate guys say you should not really strive for anything better than a good solid B. This is a great score, pretty nice clustering, and yet we have this. Now, I know you're laughing because you know the name of this class in your application. Right? Okay, and so here's the deal. On the principle that if you name it, you own it, I've named this the Death Star anti-pattern. All right, and here's how it works. I don't know you, I don't know your apps, I don't know your code, but I can tell you all about that class. Here's what it is, right? It's big. It's much bigger than the other class, on average, than the other classes in your app. It's full of conditionals. It has a huge test suite, but still incomplete coverage. Nobody wants to work on it because every time you work on it, you break something distant and apparently unrelated, but hugely important gets broken. And it represents a core, perhaps the core object in your domain. So how did that happen? Here's what I think is happening in shops all over the world who are doing OO. They start out following the design stamina hypothesis, meaning they're just throwing crappy code at the wall, trying to stay in business. Early on, they do procedures, and those procedures, okay, so early on they do procedures because of the design stamina hypothesis. Then over time, change comes in, and they just keep doing more of what they have. Because the things that are important to your application churn more than the things that aren't. The things that are core to your domain that make you unique change more often than the things that are peripheral to your domain. And so what happens in the end is by the time you figure out you've crossed the inflection point where you should be doing design, the code that isn't very important to you might be a mess, but you can fix it. The code that is really important to you defeats your attempts to refactor it from that ugly, huge procedure into OO. Many of you have probably tried to do refactorings of those big classes and failed, right? The world is littered with folks who've tried to fix that stuff and not been able to do it. And thus you get Death Stars. Okay, that's part one. Now let me show you some code. It's all in Ruby, don't worry. It'll be obvious what it does. So imagine you're writing a book. Imagine that book contains code. Imagine that you want to keep the source code separate from the text of the book so that you can run tests on it and know that it parses, and you need some dynamic way to plug code in. You could do this. This is the Ruby code to read a file and turn it into an array of strings, array of lines of code. You could do that, right? And that works for about 1 minute until you figure out that you really need version control for all the source code that you're plugging in the book. And so you'd like to keep that source code in Git, so maybe you want to tag it and have a way to reach into a Git tag and pull code in the book. The code to do that in Ruby, backticks is the way we'd shout to the command line. So you can just write a little Ruby code to use the git show command, blah, blah, blah. Don't worry if you don't understand that, right? This is a class in Ruby that I can pass some arguments to when I create it, and it can reach into a Git tag and grab me that source code. If I had that class, now I used to just be reading some files, and now I want to do either one of them. I want to read from a file or read from a tag. So now I have a conditional. That's the old code. Here's how I would get into the new code. Probably, since I'm an OO person, I would put that in a method. Maybe I'd call it lines. Then I need a bunch of cruft. Maybe I'll put it in a class. Let's call this class listing. It needs an initializer, so you pass some of these things. Many of them are optional. It's like this is how you do the setup to get either thing. I'm going to remember them all. I got getters for them. All right. That code sucks. But I mean, how much do we care? It's like a 32-point font, and it all fits on one slide that the people in the back can probably read, right? So at this point, it's like, I don't know, just walk away. Get a list. It's not that bad. If it never changed, do you care? All right, so of course the next thing that happens is another change. So what you realize is that you got all this code and files, but mostly when you're pulling listings in to put them in the book, you don't put the whole thing. Like over in your listing, you got to have it also. Your tests will run, but very often you want to grab just a part of it and put it in the code. So you need some syntax like this, like how you could print just some pages that will let you choose line numbers to suck into the book. All right, and so here's the first big point. Rich Hickey talks about this. Easy, the difference between easy and simple. Easy is to do more of what you've done. Simple is often very hard, right? And so people do the easy thing. If I do the easy thing here, well, now I'm going to have to pass line numbers in, and I'm going to have to remember those line numbers, and then now I don't have room to fit it on the slide, so I have to do that. And so here, so I have this code, and now I need to put a new conditional right there, right, where I parse through those line numbers and figure out what to do. And that means that I have to start doing some faux O here if I'm not going to do design, because I have to pretend that this is not as big as it is. And the way I can do that is like, well, I can just make a method out of that. Look, that's smaller. And if I did that, I'd probably do this too, right? I'd make one of those. And now I feel way better. All right? And so I have to remember this in a variable. So now I have to go, if you pass that line number argument, I have to go do something with that. And notice here that there's not a if-else there. I just fall through and take the default of all lines, which turns out to be important later. All right, so here's so I got to break on those commas and look at those dashes. And yeah, I don't know about you, but every time I have to write code to parse strings in that way, it ends up looking like this. And I forget what it does like 2 seconds later. It does have a test, so I know it works, and then I just immediately forget it because I find this super hard. Like I find that not very intention revealing, but look, I can just forget it. It has a name, and I could change that later, so I don't really care, right? All right, so, all right, that works for about 10 minutes. And then I realize that if I'm going to go reach into listings and just pull parts out, that I have to give you some way of knowing that code is missing. I need to put like a comment with a ... in it in the source code listing in the book, or else people are super confused. So I need to change that and do something like this, where I say like this. Right now we had this would be for Ruby code. So the pound sign is Ruby's comment, and 4 says give me indent 4 spaces, and then put a pound sign because they need to be lined up or we'll go crazy. So now I just told you I forgot this code. Now I have to change this code, which I don't really understand, but really, I know that the new conditional needs to go right there, so I'm just going to put it there, right? If I'm going to look in what I got, what I parse, and check for that thing, and I can do this, don't even bother, that puts the ellipses in. And so that works. All right? And then one more thing happens. You decide that the book needs to be, I'm going to translate the book into a number of different programming languages. And I thought, silly me, I thought that we had agreed on how many spaces would replace a tab. I thought that question was settled. What is the answer to that question? 2. Yeah, see? It's like Python, I'm looking at you. And so here's what happens when you start getting other code that you're plugging in. If you're reaching down into some code, it's possible that the sample you put in will be way over on the page. And so I need some way to left justify blocks of code to throw all those, I won't say it, all those extra spaces away. All right? And so what that means is I need justification. So if I'm going to continue to do the easy thing, now I got to wrap that. Now I'm going to pass in a Boolean argument. There's a code smell named Boolean argument for good reason, because what would you do with a Boolean argument other than write a conditional? Right? And so now I got to remember that, and then down here I need a new conditional right there, and so I'll put this up there. Now I have to remember the end of that. I have to put the else statement on there, and then I have to do that. All right. Justify was so awkward that I at least wrote 3 methods. Don't bother trying to understand them. Ouch. All right. And so here's what just happened. I'm just going to run you through the 4 changes I just made. First, we had the file or get tag. Don't try to read this. I'm just showing you the shape of the code. So there were 23 lines of code and 2 execution paths, because there was 1 conditional. Then we did the all or sum of the lines. That took my code up to 50 lines of code, and it added a second conditional, which gave me 4 execution paths. Then the comment bit didn't add much more code, only 5 more lines of code, but it did add another conditional, so now I went from 4 to 8 execution paths. And then to do this, I added a bunch more code, and I added another conditional, and now I have 16. It goes up by powers of 2. This is why your test suite is incomplete, right? What's next? 16, then 32, then 64. It doesn't take many more conditionals to where you cannot possibly test all the options. And so in 3 minutes up here, I wrote a file that's gonna, yeah, I did that, and I did that, and I'm way out here. All right? And so the moral of the story is what made things work. Like repeating the easy thing made the code very hard. And what started out making things work will eventually cause everything to fail. And the code I wrote is not object-oriented. It's just a procedure written in an object-oriented language. And it's the kind of code that rapidly becomes impossible to maintain. On that happy note, let's talk about affordances. Doorknobs. Here's a doorknob. It's a classic doorknob, right? It offers a use. This kind of doorknob is meant to be grasped. You can tell by looking at it. You can grasp it, you can rotate it, and you can push or pull on it to open the door. The grasping and the rotation is pretty obvious. It's pretty, it doesn't do a very good job in the design of indicating whether you push or pull on it. And you've all had the experience of like banging into the door because you didn't look at what the hinges were, right? Okay, here's another doorknob. I have these at my house at home. These started out as an accessibility thing, where if you don't have hands or your hands don't grasp, you can open this lever. I can tell you they're super handy, even if you could use a normal doorknob, because you can walk up to your doors with hands full of groceries, and if your door's unlocked, you can push it, like the external door swing in, so you can do that and get in your house. They're very handy. The next time you replace a doorknob, get one of these. They're surprisingly useful. It doesn't solve the problem of pushing or pulling, though. That affordance is not offered by this design. You very often see when there's failures of design to offer the useful sets of affordances, you see written documentation, which is what this is, right? And you notice that this looks like an exterior door. Like we expect exterior doors to swing in. The hinges are on the inside. Otherwise, people could take the pins out and come in your house, right? And so I'm sure that people pushed this side and they slammed into this door over and over again before someone finally put documentation on it to say pull. All right, here's a different 3 set. These don't solve the latching and unlatching problem. They're just about pulling or pushing. You look at this, tell me what it affords. You pull, right? You can tell by looking at the object. That is how it is meant to be used. This is just insulting. You would think, because on the other side of the first 2 examples, you would expect to see that, right? Now, I know why this pull sign is on the pull thing. I taught at a place in New York City, not at Stride, a place where they had like a glass fishbowl, and then a fit of symmetry, whoever had picked all the fixtures had put the pull thing on both sides of the door to the conference room. And it only went one way. And they put tiny little signs that said push. And on the other side it said pull. And I not only did I run into that thing over and over again, but people who worked there did not know how to get in and out of that room, right? Like if they'd put a push plate on the other side, it would have been perfectly obvious. So affordances. Objects in the real world have affordances. Programming languages do too. Their designers mean for you to use them in certain ways. If you want the best outcomes from your languages, you have to use the affordances that they offer. You know, Scott was up here talking about functional and the value that you can get out of using the type system. If you're using a functional language and you don't do that, you're going to cost yourself money. And the same thing is true of OO. OO has a set of affordances that the language designers intend for you to use. And here's what they are. I'm going to list them and then I'll go through them one by one. OO expects, the affordances that are offered by OO are they expect you to be anthropomorphic, polymorphic, loosely coupled, role-playing, factory-created objects that communicate by sending messages. This is OO. I'll show this slide again later for those of you who are trying to get a copy of it. So let me go through them one at a time. What is anthropomorphism? It's that thing where we pretend that inanimate things have human qualities. It's hard to tell whether the little concrete block is terrified or excited. But either way, we're going for a ride in the shopping cart. So OO, we think of objects as people. Right? I know that everybody doesn't, but I do, and I think you should. Right? They have intention. They have desires. I'm creating a play. I'm creating an artificial world where things are real. And I think of them that way. It's a big divide between functional program, which tends to be sort of more mathy, and it's a little more dry. Like in OO, the OO is Shakespeare. I don't know what functional, someone else would have to say what functional is. So that's anthropomorphism, right? We treat those objects as if they're real. Polymorphism is a word we stole from biology. It's poly, many, morph, form, not change, right? Here's an example in biology of polymorphism. This is a monarch butterfly. This is a viceroy butterfly. Here they are side by side. The monarch's on the left. Right? Monarch butterflies taste bad. Viceroy butterflies look like monarchs. Right? This is polymorphic mimicry in the biology world. We use this word, we stole this word from biology, many forms, to talk about the idea that as a sender of a message, whoever receives that message, you could have many different objects to stand in. You don't care who the receiver is, you just care that they respond to the message. The behavior is supplied by the object that receives the message. So I can get many forms of behavior without changing me, just by sending that message. That's what polymorphism means. It's a fundamental concept of OO. Loose coupling. Objects strive for independence. We need things not to be bound to one another. In this case, this is not my dog, obviously. So we have, if you think of the blue toy as the message, you could substitute dogs, right? That's what we want. We want, instead of holding onto the dog, I'm holding onto the toy, and the dog is holding onto the toy, and we're communicating across some interface where there's substitutability on the other side. The dog is not part of me. The dog is a separate object that we talk to. Role-playing. Now, I'll say this twice, sorry, and I apologize in advance. So role-playing is an anthropomorphic way of saying polymorphism. Right? Role-playing is the word that English people would use. What I'm saying is instead, all those polymorphic objects play a role. And then we can think of them that way. If you don't want to use the word polymorphism ever again, you can just substitute role-playing in its place. All right, so we think of objects that we're dealing with as players of a role rather than a kind of some type. This is another way that we get substitutability. Here, these women are all playing the role of serve-receive, and you can see parts, you can infer parts of the API, right? The uniform, readiness to receive serve, perhaps enthusiasm, intensity, clearly not shoes. All right, that's their role. All right, now, once we start thinking about interacting in a loosely coupled way with role-playing objects, we need someone to make those objects, and that's where we use factories. Factories are where conditionals go to die. That's what we want. right? And I'm not talking about this. I'm not talking about static type Java land. I'm talking about this. I'm talking about little bundles of functionality where conditionals live that pick objects, and those objects get sent messages later by someone else to invoke the behavior. Message sending. Alan Kay said if he had to do it all over again, he'd call it message-oriented programming, not object-oriented programming, right? We have objects because we send messages. We don't have messages because we don't send messages because we have objects, right? We have objects because we want to send messages. The message gives us a seam that allows that substitutability and changeability on the other side. It's that level of indirection that makes everything work. They allow what I want from an object side, that loose coupling, I want ignorance. If I can be ignorant of things, it means I can be used in new and unexpected context. And that's what we're striving for with every object we have. All right. So this is how OO wants you to think about writing code for the apps that you build. The underlying themes are ignorance and substitutability and indirection, which is really just another way of saying loose coupling. And this way of thinking, this mindset is in direct opposition to that mindset that wants to write a long procedure so they can see all the code in one place. And our job as OO programmers is to teach people to adopt this mindset rather than that other code that they've been writing because it's easy. And so let's use these principles to fix the code we have. It sounds impossible, but it's really super easy. Let's start. Oh, let me just remind you how many execution paths I have through this code. 16 right now. All right, let's start here. And so I'm just going to do the OO rant for you, right? So there's often a complaint about dependency injection. People say, oh, dependency injection is too hard, it's too complicated. Okay, look, I injected a dependency here. The value that you injected to test so that you would know which behavior to supply, it's injection. It's just too stupid to have the behavior that you want, right? You injected a thing that you then have to test and supply the behavior for. I contend that if someone outside of you knows enough to inject that, they know enough to inject a smarter thing. And so what your challenge is to figure out how to build that smarter thing. What we want to do is create a role for this thing. And the first problem we have is one of naming. What is the name of this thing in our domain? I ended up calling it source. All right? And so now I need to write the sources. I have to make up the API so that I can have multiple sources that polymorphically play a role. So I'm going to decide sources respond to lines. I need 2 of them, one for the file and one for the get tag. It's super easy to do it. You just make up new objects and you grab code in the true branch and you put it in one. And you grab the code from the false branch and you put it in another. That's it. All right? And so another core point of OO, notice what I did right there. That I had 2 things that I needed to vary. What I need to do is isolate them and make objects for each one. Once I do that, look at this. This code that I just highlighted in red is all the code in this class that's related to source. Because I've isolated the thing I want to vary, all of that goes away. Instead of injecting the get command, I can just pass in. I can inject the thing I want to talk to, and I can send it a message. And the code gets dramatically simpler. And the execution paths, the ones you do early on give you the biggest bang for your buck because of that powers of 2 thing that's going on. Because my execution paths just dropped from 16 to 8. They get cut in half every time you do this. All right? So I'm trying to, the conditional just went away, and I'm quite aware that you're probably wondering where it went. So I'm going to come back to that, okay? So hold on to that thought. Let's do the next one. It's just like this, right? You pick a name here. I called it, the variable name is super interesting here, right? Subset, I think this role is the subset. I'm going to inject, I don't need to inject line numbers. I need to inject a thing that polymorphically responds to a message and will give me a subset. Super easy. I'm going to use lines as the API again. Notice the everything subset. This is key, right? So let's look at how the code looks. What does the lines method and everything do? Yeah, it's the identity function if you're a functional programmer, right? Now what I've done is I've created a whole class to stand in for what was absent in code, which is why these things can be hard to think about. But if you can't imagine creating an object to stand in for things the concepts that were there but invisible in code, then you can't make role players. You can't make substitutable role players and get rid of the conditional. So here, so the line number, I'm just going to collapse that. This, I'm change it to the real API. I know there's still a conditional in here, but we'll get back to that. Just skip that for now. This is all the code that's related to printing lines. All of it goes away. I just inject a smarter thing, save it, send it a message. Now you notice that that's that, so I can really do that. All right, execution paths went to 4. Dependency injection is your friend, but you have to inject smart things. Don't inject things and test them and supply behavior. That test should have happened outside of you, and the objects get passed in that can respond to polymorphically respond to the message you want to send. We'll do this one just because we're here. While left just, it works the same. The none justifier is like the everything subsetter, right? It's a real thing. It's as real as the other one. Now here I need some data, so, well, here, forget that. Instead of passing a Boolean, I pass a justifier. Do that, that's really this. It's starting to look very functional, so because good OO is very functional looking, all right? All right, so the conditionals, I'm going to use this last one to show you where the conditionals went. This conditional got moved over to the everything, the subsetter that does line numbers. And it's a little bit weird because I'm not really injecting anything, like there's a loop that I'm iterating over and then choosing based on the iteration that I'm doing, which makes it difficult to inject objects from the outside because I don't know what object I need until we're in the body of that iteration. I call this clump because names are hard, but it works just like everything else. There's a comment clump and a line number clump. This code is slightly different in Ruby just because I needed some variables. I needed that spec in the input. Don't worry about it. I'm using inheritance here. If you care, you can look at the code later. It's out. This is all online. So now I'm here. Notice again, there's not an injection here that I can replace with one of those two objects, but I can nibble on my way towards solving this problem because the body of the true and the body of the false print can be replaced by those objects now. All right, so I could do this, and that makes it simpler. All right, now notice it. This is polymorphic. I'm sending the objects the same message. It's obviously they're playing the role of clump, but the problem here is that their rule about picking the rule is right here. And that means I have a bunch of dependencies here that I don't own, that someone outside of me can change that will break this code. So that's a tight coupling that I want to get rid of. But if you look at this is a factory. This is the code that ought to be in the factory. And so I can just put this in some other convenient place, maybe over in this code. I already made this clump class, so I'll put it there. I'll make a for method for the factory, which does this, which means you can pass those two variables into this thing. Once I get that, I can put a little helper method over here where you can call lines calls for, and it actually calls lines for you on the instance. And now this whole body of things can be replaced by that. All right. So we had this. We really don't care about the fourth one because that's the one we ended up with. It had 83 lines of code and 16 execution paths. Here's the OO version. There's 2 sources, 2 subsets, 2 clumps, 2 justifications, a listing class, and a number of factories, one of which I showed you, and the others you can just imagine. Over here, there's more code, almost twice as much more code, but with the exception of the factories, every class we have, no class contains a conditional. The execution path in every one of those classes there's one execution path through that code. I have 9 classes, which is definitely more. It's more stuff you have to handle, yet the largest class in this set of code has 18 lines of code. The factories, I haven't showed you all the factories, but they're as simple as the one you saw. They're shared, isolated, simple, and ignorable, and if you find factories too complicated, you oughtn't look at them. Factories are for adults. Like the people who care about that should be making the factories. The deal is you want to isolate your conditionals in factories and have the conditionals pick objects and then inject those objects instead. The last thing I want to say here before we're done, let's look at what's left in listing. This is what the listing class looks like at the end. And now, so now what it does, the responsibility of the listing class is to take that set of injected objects and control their collaboration. That's what the responsibility of listing is. Each part is super simple, but the parts combine to make a much more complicated whole. Now, I think this kind of OO arrangement, classes that look like this, is exactly what OO wants. This is what OO affords. And yet, I can tell you that when I show this code to people, when I teach and I show code like this to people, very often the pushback I get is someone will say, now I don't know what anything does. And snarky Sandy, who's usually my secret snarky self, is like, duh. Yeah, because that's the whole point, not to know what it does, right? But the truth is, like, we can be sympathetic to that. I suspect some of you have this problem in your shop. The problem is that if you're living in a place where you have faux O instead of OO, you probably can't safely make a change unless you can see all the code under your eye at once. Right? The problem is that none of your code is trustworthy. And so if you're having that problem, what I want to urge you to say and believe and teach is that the problem is not OO. The problem is that you're not doing OO. Because this is what OO looks like. It's really easy to understand. It's simple to test. I understand this code in terms of its intention, not in terms of its behavior. I don't care about its behavior. I just trust that it works. All right? Okay. So there you go. This is what OO is. Anthropomorphic, polymorphic, loosely coupled, role-playing, factory-created message-sending objects. Go home and teach all your friends like that, and teach your friends that and make your code like that. Thank you.